So today I'd like to talk about models, machine learning models, and in particular their role as software artifacts, and how they affect our software development process. So a little bit about me. Right now I'm at Twitter on the Cortex team, which is sort of the deep learning infrastructure engineering and model development team at Twitter. Previously, I was at Weebly, heading up analytics, sort of more traditional kind of big data and analytics type stuff. And before then, I was at Wolfram Research working on Mathematica, which, if you're not familiar, is a piece of software for scientific computing and mathematics and other kinds of modeling than machine learning type modeling, as well as working on Wolfram Alpha. So the motivation for this talk is really pretty simple. These are ML, machine learning models on the whiteboard, and these are machine learning models in prod. Watching you deal with sort of the mess that they've made, popping the popcorn. So for those of you who have or are about to go through this experience, sort of this talk, you can think of this talk as a way to sort of come to terms with, or sort of come to understanding of that experience. Or for people who are inclined in a different direction, you might think of this talk as kind of a call to action or a call to arms for sort of fixing the problems underlying some of the mess that I'm about to describe. So to kind of give you a taste for what we're going to talk about, here are some Gremlin interview questions. So we have component X. Component X is a pure function. Over time, it starts giving incorrect results. What happened? Or, given component X, you have no valid specification of the valid inputs or the valid outputs. Write a test suite. So these questions seem a little bit odd because they're just so counterintuitive. They're kind of against kind of our way of thinking about programs. And part of the reason why they're coming up is because although you can think of models as programs, in many ways they are programs. They take an input, they produce an output. There's also important ways in which they are substantially different from programs in the way that we use them and the properties that they have. And in particular, I want to focus on kind of the differences that matter. And ultimately, I think the differences that matter most have to do with the software development process. Sort of how we create software and kind of the expectations we have about that process and sort of the results of that process. And at the foundation of that process is sort of the fundamental properties of the artifacts themselves, the primitive units that we're manipulating during software development. Okay, so software artifacts. What kinds of things are we talking about here? So we're going to, ultimately what I want to do is kind of introduce models as a new kind of software artifact. So what are software artifacts in the first place? What are the existing ones that we kind of want to talk about right now? So ultimately, artifacts are persistent and valuable pieces of information that typically have a name, an address, and kind of structure our software over the long-term scale. So for instance, the code, the source code of your programs, typically sits on disk and eventually gets stuffed into a data artifact, which might be the Git repository, or the program artifacts that are generated from the code, stuffed in some sort of package manager or artifact manager or whatever, and then get called upon, over time to sort of implement other programs and make things run. So these are sort of the fundamental pieces that fit everything together. And kind of just to be very clear, when I'm talking about programs and code or sort of data, I'm talking about these things in their sort of static artifact form for the purposes of their talk. So of course, we know that programs can exist at runtime as processes and so forth, or that there's a notion of data that's transient, when it's passing messages back and forth or internally within a program. But for the purposes of this talk, I'm talking about these things in their sort of static, binary on-disk formats. So if we think about, well, if we're going to introduce a new thing, what does a thing even mean to exist, right? How can we distinguish, what is code from what is a program? I mean, ultimately, these are also forms of data. So how do we even begin to draw boundaries around what these primitives are? And I think, really the only way you can begin to do that is by looking at the properties and relationships that these different constructs enter into with each other. So, they may be fundamentally the same at some level, but in practice, they're different in how they get used. And those differences kind of cascade onto each other because you start building tools on top of that, and things fit together in different ways with each other. So we can kind of build a very simple model of how these primitives interact. You can think of this as like an exercise in computational thinking. That's going to help us reason about and discover what are the differences in how we use these things and where models fit in. So we can think of, at the boundary of our system, there's a human that takes a specification. We're not going to explain exactly what a specification is and produces code. So code is exactly the thing that a human produces, the instructions that are then consumable by the machine. You could say programs are simply things that compute, things that take an input and produce an output. We're not going to define what those are just yet. And then we can start seeing how, a lot of the things that we do in everyday development can kind of start being expressed in terms of these like very simple things. So, get to checkout, right? So we can have a program. It's going to take a data artifact, which is the repository, and it's going to, get the right, code artifact version out of that repository. Or building and compiling your code, that's just another program that takes code and produces another program. Or sort of the notion of indirected execution, which, if you wanted to really build this out into a full model, is very, very important. Where you have you want to execute some program, but you want to do it indirectly. So you have another program that takes as its input some program and the input to feed them through that program. And once you have sort of these ABCs, you can start thinking about how you can construct the primitive sentences or primitive words of the software development process. So a simple flow might be, okay, we have a spec. The human writes code to spec. That code goes through the build program to produce the program at hand. And then we're going to take that program and feed it through the test program together with some input data and the expected output data. And that would raise the question, so okay, we can think of human applying to the spec as being at the boundary of the system, so we can kind of let that slide. But where does the test in and test out come from? Those sort of undefined variables. So typically what we do is we bake them in with the program, right? So we sort of enter those tests as source code within the overall program that we're making. So we're going to say, so we're going to write some test code, and that test code is going to be a function of either the spec and the code, or just the spec on itself. And it's kind of interesting that we've made this choice very explicit here just by kind of tracking how all these pieces come together, right? You can imagine writing tests exclusively based on the specification of what the thing can do. And you may even do that at the very beginning of your process. Or you could write those tests if you follow another development methodology sort of after you've written your code. So you kind of take the spec of what it's supposed to do and sort of the code of kind of the implementation details, and you may choose to write your tests that way. So once you have your test code, you can kind of build it together with the actual functionality implementing code. And then you have another program, run tests, which can extract those from the artifact, the program artifact, and run just the tests and output them somewhere. Okay, so kind of the point of building up some of this formalism or pseudo-formalism is to sort of contrast it with the process of what happens with machine learning models. So the starting point of this process looks very similar, right? there's a spec, human being writes some model code to the spec. You build a model program from that code. And now you have an additional thing that we did not have before. So the model program, as soon as you've built it, it can take inputs, it can produce outputs, but those are going to be meaningless because we haven't actually trained it yet. It doesn't know how to do anything. So we can kind of imagine our sort of sample application is going to be some sort of pet image classifier, right? You know, we're going to have some awesome site where people are going to upload their pet images, and it's going to automatically know that it's a cat or a dog or, you know, a llama or whatever, and it'll automatically index and classify them and, you know, sort of recommend you sort of pets you might like or whatever. So we have our spec that's going to say something like, you know, please classify, you know, the pet images. We build a model that we think can do the job, but, you know, if we compile that and build that, it's just going to give us random predictions. So we put in a cat, and, you know, with sort of random probability, it'll give, you know, the right answer because it actually doesn't know how to do that yet. So we write the training code, we build the training program, and then the thing that creates the artifact that we actually want, which is the trained model, you know, the training program consumes the model program together with a new artifact, which is the training data, right? So this is the artifact that we want. So, you know, does anyone notice any differences from the previous step, right? So, you know, you did not have this training data artifact in the previous, sort of the traditional software process model. Just with what we've done so far, we can sort of start summarizing some very important differences between models and traditional programs. So, you know, models are atypically large and expensive to compute, which leads to a significant difference in how you actually manage those model artifacts. Also, very importantly, models are not uniquely determined by code. Right? Unlike most programs, you write the code itself more or less uniquely determines what the thing does. And models are not uniquely determined by code because you have this extra data dependency. And this leads to important differences in how you test these things, which kind of gets us into the gremlin problem, which I'll explain in a little bit. So let me expand on these points just a little bit. Models are expensive. You know, I don't know about the people in this room, but when I want to test the change of my program and I need to sort of build that program or execute that program, if that doesn't happen within a few seconds, I start getting angry. And, you know, if it doesn't happen within a few minutes, then, you know, I get very angry. Whereas with models, you know, training a model, that will take as much computational resources as you're willing to give it, which for most people tends to be on the order of 1 day, right? When you're sort of in some kind of iteration mode, you're like, please, you know, let this be done when I come in tomorrow. So you tend to sort of tune the parameters to make sure it can finish within 1 day. And once you think you're on the right track, maybe you'll run it for a week, you know, to get it to optimize all the way down. Or, you know, if you're doing something really intensive, it is not uncommon to run these models for, say, a month, or in aggregate across many computers, many, many months. Although, you know, the wall clock time will be a lot lower due to parallelism. The expense is still very high. The other thing that's true is, you know, they are not necessarily small. So some models are reasonably small, but, you know, you could easily get into the gigabytes range or higher. And then if you run, say, 50 or 100 models simultaneously because you're trying very, you know, space of parameters, this accumulates to something that's pretty big. And, you know, what that means is that, okay, you can think of models as programs, but if you actually try to treat them as programs within the tool chain, you're going to start running into problems, right? You know, I don't know about you, but I don't trust build programs to run for a month, you know, and make sure I get my really important result at the end. Or, you know, if you start uploading your hundreds of megabytes of model results into Maven, you know, how, you know, that you know, in the meantime, all the other production systems are getting the artifacts, out of the same place. That seems like a pretty risky bet to take. And likewise, things like continuous integration. I mean, if your tests run within a few minutes or tens of minutes, then sure, run all the tests after every commit. But if it takes a day or multiple days, just for one test, then continuous integration sort of no longer makes sense as a proposition in the context of sort of the whole process. So this quantitative difference in expense leads to a qualitative difference in the actual development process. So the second point, sort of the code is not enough, right? The models, the trained models are not uniquely determined by the code that you wrote. So the model behavior is ultimately determined by the training data that you used, which significantly, you don't know what the code will actually do at the time that you write it because of this. And it's also another wrench in the artifact management system, right? I mean, for good reasons, build systems, package managers, are trying to converge towards reproducible builds, having everything that's in their domain under the same roof. But if you have this side data that you can't really bake in or specify ahead of time, or really is just too big to possibly put into something like Git and so forth, then that becomes another sort of point of difficulty to contend with. So I just really want to elaborate on the testing problem because I think this kind of really gets to the core of many of the engineering problems we have with deep learning models. So we can kind of sort of work backwards from the example that we saw before and sort of see what it expands into and what information is necessary when. So you can imagine our starting point is, okay, we're going to run tests on our trained model program, and let's assume that we have some test code. So that's sort of where we would want to be and sort of where we would be in a traditional kind of software development step. So what is this trained model program? So the trained model program sub-expands or comes from applying a training program to the model program and some training data, right? So we want to test this program. The behavior of this program is determined by training another program with some specific data. And we're going to test that guy with whatever test code we supply. Okay, so where does the test code come from? So as we had before, we can say, okay, maybe it comes from the human looking at the spec and looking at the code, or looking at the spec on its own. But then, we have a problem here, right? Because, how can we write the test code for something whose behavior we don't even know yet, right? Like we haven't, when we're writing this test code, we don't have the training data yet. So how can we possibly write this, how can we possibly test this thing without knowing what the outcome of the training program is going to be? So you might say something like, okay, maybe we can kind of abstract this to something where we just write the code against the spec. And the spec will tell us what the inputs and outputs should be, and we don't care about the code or any other sort of implementation detail. But this also doesn't get us out of the problem, right? Because so kind of imagine our app, right? We're going to have a thing that's going to try to take pictures of pets and tell you what kind of pet it is. So what is your test code going to do? Is it going to you're going to type in the bytes for a cat, and then type in the bytes of the expected prediction for a cat? I mean, that's going to it's basically impossible to predict to that level of detail what this program is actually going to do, because you're trying to predict the results of this massive computation that processes all this data and does all this optimization and comes up with this very specific result. So sort of unit testing, in the way that we think of unit testing, this is really not a tenable proposition. And it actually gets a little bit worse than that. So sort of whither the spec, can we even describe what these things do anymore? So the way that we're used to thinking about these kinds of things is if the input is valid, meaning if the input conforms to the spec and the program conforms to the spec, then we expect that the output will conform to the spec. This is sort of the basic kind of reasoning mechanism that we apply to programs. But as we just saw, so we can't deduce that the program is valid without more information. And interestingly, actually the same thing is true for the input, right? I mean, we're used to having database schemas or all kinds of schemas that tell us, upfront, is the input okay? If the input is okay, then proceed with the rest of the program because we expect it to work correctly. If the input is not okay, bail. But we actually cannot do this for the case of machine learning. So, and a big part of this reason is because of this data dependency in the training step. So the model is trained on specific data. So we have a data set of like all the pets that we have that we know about, the universe of possible pets. But there's no guarantee that the input at runtime will not be different, right? You may have someone has decided that they now have a wombat as their own personal pet. And, wombats were not in the training set. So, the wombat comes into your model and it's like, I don't know, it's a dog or something. And sort of, there's really no way for you to tell that something has gone wrong. And because sort of the level at which it knows what things are sort of outside of the formal boundaries of what we can specify with rules, right? Internally, it's developed some representation of like all of these pets and so forth, based on some combination of features. But unless you understand what the model is doing, then there's no way to extract that and apply it to the data up front. So when the data starts coming in, how do you say that, well, now this is no longer matching the kind of data that we expect? So there's no way to kind of formally characterize even valid input. And this is something that you might call the model decay problem, where sort of you train the model, you put it into production, it's like performing well, and then it'll sort of slowly start to dip and start performing less well. And that's because the underlying behavior of the system where it's applying sort of the input data, the distributions in that input data are changing as patterns in the real world are changing. Different users with different interests or different specific memes or different specific data is flowing through the system, even though all the formal characteristics in the sense of what we think of as kind of traditionally correct software engineering stuff remain the same. The metrics all look good. There's no sort of actual problem with any code. It's just that the nature of the content flowing through has changed. So this is sort of my reaction to this set of facts. This is really not how I would normally think of software behaving. And these kinds of situations are quick to drive one into statistical thinking, right? Which might be something along the lines of you're saying there's a chance. So the statistical approach, and there's more or less no escaping the statistical approach, but it's no savior either. So you're like, okay, there's obviously no way I can write an explicit unit test where it's like this input equals this output. But you could imagine saying, okay, out of all the pets, I want at least 80% of them to be classified accurately. Which particular 80% might be subject to change, but that's sort of what we're going to define as correctness. But that sort of only kicks the can down the road, because where does that number come from in the first place, right? It's sort of like if you just show up and throw a number and say we're going to get 99% of all the pets right, or whatever that number is, it doesn't actually mean anything, right? Unless you know what empirical performance is possible, you're just picking a number that doesn't mean anything. It's like something that someone who's never used the internet, trying to specify to you, the implementation requirements of a website. The accuracy, the performance of these things must be discovered, not specified. And once you do that, once you discover these numbers, or if you have a strong prior, you can use them for regression tests. But that doesn't really serve all the purposes that testing or other kinds of correctness verification typically serve. So for instance, it doesn't help you with debugging, right? You have some system out in the field, it starts misbehaving. One of the reasons you have these tests is then you can kind of go in there and be like, okay, start reasoning, start pinpointing where exactly the problem is. But sort of this kind of really high-level statistical approach is not necessarily going to help you with that. Nor is it going to tell you sort of what you can achieve in the first place. And you still have the tooling problem, right? I mean, there's all sort of the nitty-gritty of how do you actually make these things work as sort of software artifacts. Doesn't go away. Okay, so how are we doing on time here? 10 of 12? Okay, great. Okay, so software artifacts. So I've sort of explained, or tried to explain, some of the differences between machine learning models and what we think of as traditional software artifacts. But sort of so far, now we just sort of have a bit of a mess on the floor. There's sort of problems. There's not really good solutions. And I think, to figure out what the real problem is and sort of how we might solve it, we have to go up the hierarchy a little bit and think in terms of the overall software development process. So, in other words, if we're going to bother trying to fix this problem, what are we actually trying to achieve here? If we're going to break out models as sort of a new software artifact, well, what kind of properties should they have, and what kind of purposes should they serve? And I'd say, the most important thing is they need to serve an empirical development process, which is, a development process based on experiments and sort of much closer to the scientific method. And sort of when people talk about the problems associated with models, they often talk about, oh, models are this black box. They're complicated, we don't understand what they're doing, and because we don't understand what they're doing, there's all these problems, right? You can't sort of, it's hard to engineer them, it's hard to debug them, it's hard to predict sort of when they may apply and when they not apply and when they're starting to fail, or and so forth. And I would say they're not wrong in the conclusion that if you don't understand what it's doing or how it works, then it's very difficult to engineer with that artifact. But I think they are completely wrong in the sense of thinking that it is a black box by nature. So there's lots of things that we used to think were black boxes. Various aspects of the nature of the cosmos, or sort of the physical body, kind of the mechanisms of life, so forth. Lots of things people used to think are black boxes. But what you need to do is you need to open them up, right? You need to start poking at them and see what they actually do, build intuition, do experiments, and then sort of continue the process of sort of building knowledge of how things work. So say, open up the box, right? Engineering requires understanding of properties. These properties are empirically determined. This is same thing for structural engineering, right? Like you got to know the properties of steel, the properties of concrete, the properties of these basic materials if you want to do something with them. And I'd say this is actually a major challenge to the software engineering process, because this is not how we're used to working. So software engineering privileges deductive over empirical reasoning. And this is really built into the whole field. So the thing that we do all day, right? Pretty much what we do all day is simulating a computer in our head. So that's deductive reasoning, right? You're like, okay, I have a list, I have a function that takes a list and returns like some other type. And then the next function consumes this type and returns some other type and so forth. So it's sort of this chain of reasoning and inference of saying if this then that, and making these deductions from the general principles to the specifics of your program. And that's built into our programming languages, into our tooling, and into our human processes around us engineering these artifacts. So sort of the happy path is the deductive path, right? It's so nice when you're in your IDE and it auto-completes the package import, or it auto-completes sort of does the type inference for you, or quickly runs the tests for you, so you don't have to sort of manually go through those like deductive steps, and it'll kind of catch you from not being able to deduce correctly everywhere all the time at the same time. Now that's when you're on the happy path. When you're not on the happy path is when you have to do an empirical experiment, right? If you actually have to write code, if you have to write code that's not part of the actual programming of the actual program that you're developing, but it is only there to give you information about the program that you're developing, then you're not on the happy path. Then it's like, oh my God, this is like such a pain. Please, can I just write a print statement somewhere to give me that minimal extra piece of information to perform the next deductive step? Oh, the problem is not in this branch, it's in this branch. And to be fair, sort of data and modeling, it's long obscure, right? This is it's not been in the mainstream, of programming, and these concerns, simply just did not exist for many programmers. So, for a variety of reasons, software engineering has privileged deductive reasoning over empirical reasoning. And just to give you sort of a simple piece of evidence that this is the case, think about IDE'S or your favorite, development environment. Festooned with, type inference, step debuggers, integrated tests, all these tools to help automate the deductive reasoning that you're doing, all the simulating of the computer in your head where you're like, oh, I wish I could just automate this, and then the IDE just does it for you. Lots of that stuff. But where's the support for data analysis or running systematic experiments, right? I mean, how hard is it to just like run some benchmarks on different versions of your code and just get a plot from that? Is that something that's integrated into IDEs, or sort of something people just can whip out willy-nilly? Generally not the case. Let alone sort of more complex type reasoning analysis. So a somewhat more involved example, which I think kind of gets to some more core issues, is something I might call the linear successor model of software engineering. So the linear successor model. So this is sort of the notion that a product is a linear sequence of programs. And sort of program n+1 subsumes program n in its functionality. And what the linear successor model does is it solves for the problem of the concurrent construction of this sort of product sequence, right? So you have like a team of people, you want to push out versions of the product as fast as possible, and the linear successor model tells you how to stage that work in order to pump out these versions. And the way it does that is you have a high branching factor at the leaves, sort of the individual branches of the developers, followed by a rapid convergence to the production artifact. So let me just kind of step through an example. So you can imagine you have one product, right? That's sort of the product of your company. You may have three classes of artifacts, dev, staging, and prod. Prod is ultimately the product. But you have many individual code branches where features are being developed, bugs are being fixed, kind of conflicts between other people's branches are resolved, and so forth. But very quickly, all those branches merge into master. And then, for instance, CI builds, runs tests, puts into staging, and then eventually someone presses a button or something decides that this is now the new product. So so this is more or less, there are many different versions of this process, but it's more or less kind of the standard way that things are done these days. So what are the assumptions and the consequences of this model, and how do they compare to sort of the needs of an empirical development process? So the first assumption is artifacts are not valuable in and of themselves, right? Sort of, the thing that's ultimately valuable is the product. And anytime someone needs the product, they can just ask for it, and they basically get the latest version. But the artifacts themselves, in and of themselves, are not valuable. And this conflicts with our need with experimental results, which are in fact very valuable, and we can't afford to just sort of toss them to the side. Another assumption is that branches can be isolated, right? Sort of ideally, work on features can happen independently, and then ideally merge with as little sort of conflict or overlap as possible. Whereas in an experimental workflow, comparison is sort of one of the essential essences of what you need to do, right? And this may sound like a simple thing, but it's actually an incredible pain, right? If you imagine having to, so somewhat realistic case might be, you're trying to performance test your code, and you're trying to make improvements to make it go faster. So what do? Are you going to have like one branch, are you going to sort of make a branch for each version of your test where you're like, okay, I'm going to try this optimization, try that optimization, sort of possibly branch from there, collect all the data points from each branch, and then make an Excel spreadsheet with like each branch, SHA, and then the corresponding performance. And then what happens when you realize that you set up your experiment incorrectly and you need to generate data in a different way? Then you're going to go and like check out each branch, fix the thing, run the thing over again. I mean, it's a total mess, right? So the alternative to that is, well, are you going to have it all in one branch? Are you going to have like n versions of that piece of code in one branch, and then once you figure out which one is the most optimal, throw the rest of them away and just merge the winner into master. And sort of all that work you did is sort of lost to the sands of time. The branching and sort of branches in the branching model is all about isolating things. It's not about being able to easily compare things. And sort of when you get out of, and when your need is to compare things, it's sort of not a very good fit. So yes, so the way that we develop software sort of assumes that the goal here is to have simple and repeatable comparisons of all these possible variations, sort of at the kind of unit test level, for instance. Whereas experiments require comparisons in complex and ad hoc ways. So one of the consequences of this is bit rot. So sort of any code that's not attached to the head, sort of to the head of the product, is ultimately going to rot away due to underlying changes that are happening all the time. But experiments are typically not attached to the product head, right? They're sort of things that generate knowledge and information, which then will generate new models, among which one of them will eventually be integrated into the product. But all this other stuff still needs to hang around, because when you develop the next model and you're trying to figure out what it does and how its performance compares with other ways of doing things, you need to continue to be able to load all those previous models that you developed, right? This is sort of the empirical process. You need to be able to have access to those old experiments and not have them rot away from underneath you. There's sort of another thing that you might call sort of prod coupling, or other people might call it just bad design, but definitely is pretty prevalent, which is any code that is not directly related to the product execution is marginalized, right? If you're not on the code path, if you're not directly on the code path between the user making the request and the user making the response, sort of, that's sort of the code that gets pushed off to the side and kind of creeps around the edges, because there's people tend to prioritize the prod code path at the expense of everything else. So if you need access to data in a certain way, it could very well be that, someone implemented that function together with the message queue, and the only way to get that thing to run is by pushing messages through the message queue. or it's in the database, or sort of whatever. There's all these couplings that happen in prod, where if you try to do things in an experimental setting where it's like, let's try all possible parameters, and then you're like, wow, there's literally no way to get the information into where it needs to go and then back out, then you tend to be in a very bad place. Experiments need flexible and direct access to functionality. So this is sort of the Katniss mode, the sort of Katniss empiricist mode here. So empiricism, this is the final plea for empiricism. So, I think this is something everyone can agree with at least, deductive reasoning. For all things for which it works well. And empirical reasoning, for all things that we cannot deduce, it's all we got, right? And I would argue that the set of things that empirical reasoning will apply to in software engineering and computing in general is only going to expand. As systems get more complex, as systems become more difficult to predict and understand, empirical reasoning is going to start to become a more dominant way that we approach these things and figure out what's going on and what we need to do. But this is going to be a big project. It's not just kind of fixing Maven or getting better build systems or having more research as to how models, deep learning models behave. It also involves how do we communicate results, all these steps of reproducibility of the scientific process. But fortunately that ball is rolling. So for instance, what's an alternative to IDE'S or an alternative to Git for storing code? So there's things like notebooks, which after 30 years have finally become popular. So IPython or Jupyter notebooks are now becoming the kind of de facto way of doing data science and modeling and basically any kind of thing that's of an experimental nature because they just so much more clearly capture this flow of, I need to do an experiment, I need to see the results, I need to communicate those things to other people, I need to go back and reference these things between each other and not have to kind of be within the constraints of, the linear successor model of software engineering. There's things like FB Learner at Facebook, and other companies are developing similar things, which are trying to solve this overall model bookkeeping, model computation, model result analysis package series of steps. So sort of the series of steps that we were sort of implementing in our little pseudo language, kind of made into more of a development environment in its own right. Or even just at the fundamental level, things like data flow processing systems and build systems, seem to be converging, which I think will definitely be, the way things go in the future and sort of help solve that problem for us. So, there's a lot of positive things happening. There's still a lot of work left to do. And I hope that this talk kind of encourages people to either think about and help dig into some of those areas. And sort of in particular, sort of, on the question of, what are the actual problems? So, among things that are happening, people are starting to ask these questions of, in which ways are machine learning models different? How do they impact the software engineering process? And trying to identify, the actual problems that we have. So this is me. Follow me on Twitter. Thank you.
We can do a few questions.
Hi, thank you for that. You mentioned notebooks and some other solutions for communicating ideas. Do you have any suggestions for how data science teams can work with their engineering teams to then integrate those models? I mean, it's a hard problem.
So you mean integrate the models back into the product? Yeah, so that's a very good question. So because of this sort of split between these two worlds, notebooks are very useful for scientists. They're sort of less good as themselves being software artifacts, sort of ironically in a presentation about software artifacts. Notebooks themselves are sort of not necessarily great software artifacts. So I have a lot of ideas of how they can be better. I think ultimately people are going to go back to a more text-based model, at least for authoring, and that might be presented differently. But I think it's just going to take a long time to have those things be integrated in a way that makes sense. So I can't really make any predictions as which one will work out.
Hi. You mentioned that testing and validating models is something that is not straightforward as we do with software. Which is the testing and validation process that you normally follow with your team?
There's a few. I think you have to think about testing a few different kinds of things. So, as I mentioned in the talk, one thing that you absolutely can do is sort of regression test in different ways. So once you've determined that such and such performance or accuracy is possible, then you can make a test that's like, okay, did we achieve this accuracy over this large data set? The other thing that you can do is, for a very specific model, say you've already created a model, you can have regression tests to make sure that it continues to perform exactly the same way. So this data comes in and this data comes out. But that's not something that you would ever want to build by hand. So what you would sort of typically, you kind of want this to be an automated process of you create a model, there's a bunch of analysis that happens on the model, sort of that analysis sits off as its own artifact. And then, the next time you create a model that's in that same lineage or with some regularity when there's changes in source, you sort of want to run something that's kind of like a integration test. Then you take all these analyses of the different models and then you compare them with each other. And according to some kind of policy, either say, accept or reject what happened. So, if it's the same model that you're testing, then you want the results to be exactly the same. If you're testing a new model that's developed with a new methodology, the results cannot be exactly the same, but that they must, be at least as good or sort of conform within the boundaries of the performance. So, really, it's all about sort of automating these processes of analyzing the model, putting data through the model, seeing the results, and then sort of comparing what those things did.
Okay, let's thank the speaker again.